Hello, I'm Dr. Deborah Campbell, and I am creating this video as a companion piece to Patrick J. Hurley's A Concise Introduction to Logic. We're using the 13th edition now. And this video particularly goes with section 6.2, which introduces the notion of truth functions or truth functionality for the logical operators in propositional logic. And again, I'm going to spend more time on what I call the tricky bits. So hopefully you've been learning that, you've been reading about and learning that the 5 logical operators that represent the not or negation, the and or conjunction, the wedge or disjunction, or either or, the horseshoe, the if then or conditional, and the biconditional, the if and only if. How they are symbolized was discussed in section 6.1, and now you need to learn how they behave when they are combining statements for which you know the truth value. So for example, let's take the small letter P, which always stands for just any simple statement. For any simple statement, if the truth value can be true or false, then we have to know how does putting a not in that statement or in front of that statement affect the overall truth value of the statement. So let's say we had a proposition like Joe Biden is president. Well, that's true, but then if somebody said he is not, Joe Biden is not president, that would be the logically compound statement, not the case that Joe Biden is president, and we would have to say, no, that's false. Because if this proposition is true, then negating it makes it false. If you start with a false proposition like Hillary Clinton is president, which we know is false, then if somebody says she isn't, well, that makes that clearly true, right? So this is called the truth functionality of the negation symbol. Now, your book lays it out in tables to say, these are the logically possible combinations, and this is how the logical operators function when operating on a proposition or combining propositions. So they say that these tables supply the definition for how a logical operator like an and or functions. I do not stress memorizing the tables, and you certainly don't want to have to keep looking back at the tables. So what I'm going to do is explain what I think of as the general rule that you can internalize for each of these logical operators so that as soon as you look at any statement with that logical operator, you'll immediately know how to calculate the truth value. So for example, in a conjunction, you have 2 conjuncts, a left conjunct and a right conjunct. So there are 2 statements in a conjunction like Joe Biden is president and Jill Biden is first lady. That's a compound statement, it's a conjunction, and in this case we know that both of those statements are true. So the first line of the truth table, that's the definition for a conjunction, has both statements being true. Well, obviously in English, if we say both statements are true, then the whole thing is true. However, in English, if any part of an and statement is false, we have to reject the whole thing. So if we tried to say Joe Biden is president and Hillary Clinton is also president, somebody would say, no. Part of that was false, so the whole thing is false. So the general rule for the conjunction, again, you don't need to memorize all the T's and F's in the table. The general rule for an and statement in English or conjunction is that both parts of it have to be true for us to say that compound statement is true. So how would you fill out the table? Well, it's pretty easy. They both have to be true. Every other combination is false. Okay? So that's the rule. And so that way, whenever you run into a compound statement of something like Joe Biden is president and Donald Trump is president, you would know that if this is true and this is false, well, the whole thing is automatically false. Okay, the or is also pretty easy and straightforward. In English, when we make a claim that has an or in it, we're saying it needs to be at least one or the other. although sometimes it could be both. And that's coming up in 6.3. But for right now, the or statement, it's one or the other, but it could possibly be both. So we could say either Joe Biden is president or Jill Biden is first lady. Well, both of those are true. So if at least one has to be true for it to be true, actually the whole thing is true. You can see how or is sometimes used inclusively, like I'm going to have a banana or an apple for lunch. You can have both, and it would still be true. If I had said I was going to have one or the other, if I had both, it would still be true. There are some ors that are exclusive, like dead or alive, but that has to be symbolized differently. If I want to symbolize in logic that it's an exclusive or, it actually would have to be, you would have to say something like, Joe Biden or Donald Trump is president, and it's not the case that both are president. Okay? So keep in mind the exclusive or has much longer symbolization. The truth table for the or, the either or, the unless, is just, it assumes that the or is inclusive unless otherwise noted. So how do you fill in the truth table for the or? Well, because we said that all you need is for one of the disjuncts to be true, for an or statement to be true, then any time you have a T on either side of the or, it's automatically true. The only combination that makes an or statement false is if they're both false. So if someone were to say, either Abraham Lincoln or George Washington is currently president, well then, obviously that's false. Okay, so those are pretty straightforward. I'm going to skip over the conditional for a moment because it's a little trickier. I want to go to the triple bar, the biconditional or equivalence. And the way that operates is that it is true when the statement on either side are the same. So to the left and to the right, if they are both true, it's true. However, if they are opposite, they obviously can't be equivalent. You can't have a true on one side of an equivalence, a false on the other, and say that's a true statement. Okay? So the two in the middle are false. Of course, if they are both false, then they're equivalent. So if you have a false on either side of the equivalence, that's also true. You're saying the connective, because we're talking about how the operators work and how the ultimate statement, the truth value of the ultimate statement will come out. Okay, so let's go back to the horseshoe. In that case, when you're dealing with the horseshoe, there's an example in your book that says, if you get an A on the final exam, then you will receive an A in the course. Now, that's a hypothetical. There are two statements. You get the A on the final, you get an A in the course. So, how do you know when that's true? This is, again, a little bit trickier, but let me explain it using that example. And again, this is in your textbook as well. So, if it's true that you get the A on the final, and it's true that you get the A in the course, then obviously the conditional claim that I made, the implication, turned out to be true. So true implies true, pretty easy and straightforward that that's true. All right, if you have a true antecedent, like I say, if you get the A on the exam, you get the A in the course. If you get the A on the final, and I don't give you an A in the course, then it's clearly false, right? I've said that the antecedent, the sufficient condition was met. I did not give you the A in the course. Clearly what I said was false. Now, the other two are the tricky parts. What if the sufficient condition or the antecedent condition isn't met? So let's say you don't get an A on the final, but somehow you still get an A in the course. Maybe you did extra credit or something. Well, the conditional claim that I made earlier, if you get an A on the final, you get an A in the course, there's no way to prove that false, right? You didn't get the A on the final. I still gave you an A in the course, so what I said still has to be deemed true, right? If the antecedent condition isn't met, then whether I give you the A or don't give you the A, what I said earlier still has to be deemed to be true. Because if you don't get the A on the final, and I don't give you an A in the course, then obviously what I said is still true. What's the general rule to remember for the conditional statement? It's pretty easy. The only time a conditional statement can be proved false, because it's a hypothetical, is when the antecedent condition is met, it's true, and the necessary or consequent turns out to be false. So true implies false. It's the only time a conditional statement's false. Okay? So just to recap, what were the rules? For an and, they both have to be true. For an or, only one needs to be true. And that's only false when they're both false. For if then, only combination that is false is that a true implies false. Every other combination is true. And for if and only if, the rule is if they are the same on each side, it's true. If they're opposite values, it's false. The equivalence doesn't hold. Okay, so hopefully that helps you to, again, instead of trying to memorize all the T's and F's in the table, just think about the rule when you're looking at calculating the value of a compound proposition. So the exercise sets, just a few pointers about those. The part 1 exercise set is about identifying the main operator of a compound statement that has more than one operator. So you always look for the logical operator that's left outside of any parentheses, braces, or brackets. That's the general rule. So looking at this long expression, which I'm going to go over in just a minute, the one operation, the logical operation that's left outside of everything else is this one. So that's going to be your final answer. That's going to be the last operation you do in your order of operations. So part 1, they want you to think about where's your main operator? What's going to be your final calculation? And everything inside parentheses has to be done prior to that. Okay, so that leads us to part 2, which they want you to practice the general strategy for calculating the value of a compound proposition. In your book, they have what I call the order of operations. They have the general strategy. And the general strategy is when you're trying to calculate the value of a compound proposition, you first have to know the truth value of the individual sentence letters. That's step 1. So in the very first example in this exercise set, I think they say it's not the case that Hitler ran the Third Reich. Now, in order to calculate the value of that, you have to know whether Hitler ran the Third Reich, whether that's true or false. So in these part 2 exercises, you may have to look some of these up. Hopefully you know that Hitler ran the Third Reich is true, but they put a not in the sentence. That makes it a logical compound, and the final answer is false. Okay? He did run the Third Reich, so if they say he didn't, the overall value is false. Now, I want to recommend that you don't just look at the whole expression and stick a false under there, like somewhere in the middle. Instead, always make sure that you follow the order of operations. Assign your truth values to the statements first, and then take care of the logical operators. Okay? So if H is true, not H becomes false. Here's another simple one. I think problem number 2 is something like Nixon resigned the presidency and Lincoln wrote the Gettysburg Address. Okay, Nixon resigned the presidency. Again, you might have to look it up. I happen to know that's true. Lincoln wrote the Gettysburg Address is also true. And so knowing the general rule for the and, it is true when they're both true. It's true on each side. Main operator is true. Okay? So the general strategy is you assign the truth values to the sentence letters first, and then work on the logical operators. You take care of negations first, and then other operations like and, or, if, then. Okay, so how does this work out when you get to a really long, complicated statement with a lot of operators? So I've just made one up here for you, to walk you through it. And this is in 6.1 part 3. In this exercise, you don't have to know the truth value of the statement yourself. They have stipulated the truth values to say, for practice, we're going to say A, B, and C are true, and X, Y, and Z have the truth value of false. All right? So the truth values of these practice exercises in part 3 are just stipulated. So following the order of operations or the general strategy, first we're going to say A is true, B is true, Y is false, and X is false. Again, A, B, and C are true, X, Y, and Z are false. We're just stipulating that. Okay, according to the general strategy, the next thing you look for is you take care of any negations in front of sentence letters. So if Y is false, but it has a tilde in front of it, you have to change that value to true. Now, I'm going to drop down one line for each operation that I do. They give you examples like that in the book. Later on, you'll start just calculating it all out on one line as you get faster and faster. Okay, so if Y is false, not Y is true. All right, now, if you have no more operators in front of letters, then the next step in the strategy is you start working inside the parentheses. The general strategy is to work from inside the smaller operations to outside the larger operations. In this instance, it would resemble a math problem a little bit. I want to caution you about making too many comparisons between math and logic. The philosopher Frege rightly pointed out that at the most fundamental level, math and logic can all be reduced to the same thing, and that is set theory. But for our purposes, remember, we're working with words and statements. So there are going to be some similarities to math, but we're not working with numbers. We're working with statements that have meaning and truth value. So we can't always say it's going to work out the way you would work a math problem. But in this instance, the order of operations, yes, it is similar. All right, so now we work inside the parentheses. So this is a dot, true and true. Again, knowing the rule, not looking at the tables, but knowing the rule, is this going to work out to be true, okay? And over here, true and false, again, we would say is going to work out to be false, okay? If you're having to look back at the tables every time, then you're not ready to be doing the exercises. Trust me on this. The first thing you want to do is not memorize the table, but do enough practice problems to learn the rules for the and, the or, the if, then. Then when you're doing these calculations, it'll go very quickly. Okay, so we've done inside the parentheses. The next step is to take care of any tildes preceding parentheses. So if we have a true for our final value in here, but we have a false out there, then we have to make that whole thing false. And on this side of the wedge, this was false inside, so that becomes true, okay? So we have to take care of negations outside of parentheses. Now we can calculate the value of this operator that's within the brackets. So false or true, because it's an or, the rule is you only need one to be true. So false or true is going to give you a true here. But, oh, what's our main operator? Well, there was another tilde outside the whole thing. So this true ultimately becomes false. And you want to circle your final answer. You want to follow the method and create good habits. If you start looking at things and say, well, that's not H, I know that whole thing's false, so I'm just going to put a false in the middle. Then when you get to the longer expressions, you won't be able to easily follow what your calculations were. Okay, well, that's the tricky bits of 6.2 truth functionality for the logical operators and computing the value of a longer proposition. I hope that you spend enough time on 6.1 and 6.2 to prepare you for truth tables in 6.3. Getting a good foundation is the key to all of this. If you find that you're having difficulty anywhere along the way, back up. Going forward does not help. You always need to take the time and back up. That's going to be the best use of your time. And email me if you have questions. All right, thank you.